Okay, guys, let's go over the 2017 AP Physics 1 free response question 3, which is supposed to be rather similar to the question on your online exam, one of your two questions worth about 60% of your grade. Should be exciting. It's not that bad a question. It's a little funny. I tend to overcomplicate or give more than it needs. But let's take a look at it. So basically our situation, we got a rod attached to a pivot. The rod is much heavier than the disc initially for the first A, B, and C. And you got this disc flying up, it smacks into the rod, sticks to it, and then the thing rotates. And you want to figure out how big you should make X to make the angular velocity afterwards as big as possible. Now, initially I started being like, well, your ball's angular momentum is its mass times velocity, MVR. If you don't remember how L equals MVR, L is like momentum is mass times velocity, and so the angular equivalent is the angular equivalent of mass, which is I, and velocity is the angular equivalent is angular velocity. For a point mass, which we kind of have here, I is mr squared, and the angular velocity is, you remember, like d equals theta r, v equals omega r, etc. So you could say omega is v over r. Anyway, we can cancel out one of ours and we end up with our lovely formula here. So that's just quick if you forgot about that one. Anyway, so since the angular momentum is mvr, m's held constant, v is held constant, we want to make r as big as possible. And then you can do L before equals L after. Your mvr, your angular momentum before, is going to equal your I omega after. And the amount the ball will add to the moment of inertia of the rod will be not very much, because the I of the rod is, the mass of the rod is much bigger. Anyway, so that's how I was going to explain it. Here is how they recommended it, which is much simpler. They're not looking for that in depth. So if you go to the solutions, which I've also posted, sorry. So the disc exerts a greater torque on the rod when it pushes the rod farther from the pivot. True. You could also have just said the disc has a greater angular momentum when it's farther from the pivot, which is what I was getting at. The disc loses almost all its speed during the collision, hence gives the rod almost all its angular momentum. So the rod ends up with more angular momentum when it hits the disc, when the disc hits it farther from the pivot. So that is the gist of the kinds of explanations that they're looking for. So you don't have to get as complicated as I was. Though it becomes useful later. Anyway, so for part B, a student says, hey, he finds the following question for the post-collision angular speed omega. Basically, does this equation that this kid found on the internet have the expected dependence as reasoned in A? I said, hey, you make X bigger, your angular speed gets bigger. That's all they're looking for. Because here I mentioned that if you move it to the right, then X gets bigger. So this has that dependence. So if we move X to the right, our angular speed gets bigger. So that is all they're looking for. If you go and check your official answer, it's, I don't know, overly simple for my liking. But according to this equation, your angular speed increases with X, a bigger X produces a bigger angular speed, and this agrees with my reasoning for part A, where I said a bigger X creates a bigger angular speed after the collision. So yeah, let's just say that it's consistent that way. And let's try C. And then for this guy, this one's sort of a funny one. It says you've got this other student deriving an equation for the post-collision angular speed omega of the rod. He makes a mistake and comes up with this garbage formula. Without deriving the correct equation, how can you tell this equation sucks? So basically you just kind of look at it, and a lot of the issues, if you think about the difference between the two, are I is kind of in the wrong place. It's got the reverse dependency, and mass of the disk has the reverse dependency, so we got to kind of think logically about why this has to have the reverse dependency. So what this is saying is if you make the angular momentum of that rod just stupidly huge, if you make it the biggest, like heaviest like thing of lead ever, that'll increase your angular velocity after it gets hit, regardless of the mass of the disk, which is totally not true. Things hitting larger things don't move them as much, and they also don't rotate them as much. So you can have an argument kind of based on that. It also has an inverse dependency to the mass of the disk. So as the mass of the disk goes towards zero, your angular speed after it hits that bar gets faster the smaller the mass of the disk, which makes no sense at all. You throw a smaller thing, it rotates this big heavy door or whatever, or rod or whatever it is, faster than a bigger disk thrown at the same speed. That does not make any sense at all. Anyway, so those are the easiest ones to argue because it's got reverse dependency based on the actual formula. So take a line of reasoning similar to that. Okay, for parts D and E, we do not assume that the rod is much more massive than the disk. So for D, immediately before colliding with the rod, the disk's rotational inertia around the pivot is mx squared. Remember, it's like a point mass, so it's mr squared for moment inertia. Anyway, and its angular momentum with respect to the pivot is mvr. M disk v naught x, mvr. Divide an equation for the post-collision angular speed of the rod, and blah, 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 blah. So this is pretty easy. It's just conservation of angular momentum. You got a certain amount of angular momentum before. It's equal to the angular momentum after. And so you just do your MVR before because you got your point mass. Mass of it times its velocity times the distance perpendicular from the pivot. And remember the trick that you can calculate your angular momentum if there's no torque acting on it, like its angular momentum here is the same as its angular momentum on impact, and on impact its velocity and its radius are all perpendicular to each other. So choose that point to calculate the angular momentum, and you can just use MVR. Anyway, coming back to it, so here's our angular momentum before. It's going to equal our angular momentum after, which is the combined angular momentum. You've got the angular momentum of the rod like it was before, plus it's got a disk stuck to it. So the mass of the disk times the distance from the pivot squared, the mr squared part contribution. Anyway, so you got your total angular momentum times the angular velocity. And then rearrange that, and you got this beautiful guy. It's kind of like momentum divided by mass gives you final velocity kind of thing. If you got two things sticking together, basically the same idea for angular momentum. All right, so for the last part of the question, it says consider the collision for which your equation part D was derived. Blah, blah, blah. Except now, suppose the disk bounces backward off the rod. So you're asking, hey, what's happening to the post-collision angular speed of the rod when it bounces off compared to how it is when it sticks? and it's totally going to be greater than. I said personally, because it doesn't increase the angular or moment of inertia of the rod. It's not sticking to it, so it's not contributing to that. And now the angular momentum of the rod is equal and opposite to the change in angular momentum of the disc. So here's the change in angular momentum of the disc. I threw in this little negative sign. I didn't want to get stuck on it, so I wrote it small. So it's basically M change in V R, and the magnitude of this change in V is going to be larger than V naught, which it was kind of originally, or pretty close to that. Anyway, so this is guaranteed to be larger if it bounces off. I think in the official answer key, they use, after the bouncy collision, the disc has angular momentum in the clockwise direction. To keep the system angular momentum constant, the magnitude of the rod's counterclockwise angular momentum must be greater than before. Yeah, so same kind of idea. Anyway, hope this helps. Give it a practice. Wrap your brain around this kind of question answering. I'll try and find you more stuff like it. Be well, and thanks for watching.